Okay, good morning, everyone. Hope you're all doing well. We are going to carry on directly into Lecture 9 on information spaces this morning, which will finish up our theme on how to go about approaching the design of interactive systems. We will probably finish Lecture 9 today and start in on the next theme of the course, cognitive psychology. As I mentioned last time, we're going to look at just a few aspects of human cognition that are relevant for our discussion about HCI. We're going to look at 4 different aspects of cognition, and I have ordered these from, as usual, the most objective aspects of cognition, those aspects of cognition that are easiest for us to measure, up to the most subjective aspects of human cognition, which are not so easy to measure, and specifically in Lecture 13, we're going to talk about affect, or psychology's word for emotion. Any questions about deliverable 6? Just as a reminder, as I mentioned last time, you are going to be downloading and using data sets from the other students in the class, which you all developed last week in deliverable 5. So we are grading deliverable 5 as we speak, and we will drop those data files into the directory that you're going to draw from in deliverable 6. They're not there yet, but we will get them there today or tomorrow. Okay, everyone can hear me okay, I'm assuming? Please type into chat if you can hear me, just so I know. Thank you. Okay, all right, so back to information spaces. We started last time by talking about the front end of an information space, which is the user interface, and we looked at some familiar ones from last time: command-based user interfaces, typing things at the console, GUIs. We looked at the React table. Which was a tangible interface. We looked at Bump Top, which combines a physics engine with an operating system interface. We ended last time by talking about you cannot sign the attendance sheet. Others can, so I think Kay, just give it another go. So in user interfaces, obviously we have lots of different elementary building blocks of a user interface. And if we're thinking about GUIs, those different elements of a GUI, like windows and menus and pop-ups and buttons and so on, they are designed to support different ways of thinking. So windows allow for spatial organization or spatial cognition. Menus help us in that we usually try and organize things hierarchically. If you can't remember exactly where a function is in an app, you usually know generally where in the menu hierarchy to go looking for it. Okay, if you're an advanced user and you want to perform task A, take the results from A, feed it into B, take the results of B, feed it into C, and so on. You usually want to work at the command line where you can pipe or attach together a sequence of actions, so thinking sequentially. Pop-ups are there for contextual organization. A lot of us have a lot of things we need to remember, so we often organize our desktop or our apps or our phones so that they'll remind us when important things happen. Okay, so all of these are ways of organizing information in a two-dimensional interface, which provides a view onto an underlying information space, a complex constellation of information and data and connections to other people and so on, that the interface makes it easier for us to navigate that space. So we're going to switch now from user interfaces, which we've spent most of our time talking about, to what's behind the interface, the information space. Okay, so you'll note the name space. A space is filled with an information space is filled with objects and data. People enter the space, they observe the space from the outside, they navigate through the space to accomplish various tasks, they find each other inside the space, and as the name implies, the most obvious example of an information space is cyberspace. right? As we know, the internet is literally a network of devices spread over the surface of the Earth and satellites in orbit overhead. So there is, in a sense, a physical network, objects out there in the world that are interconnected to one another, and collectively they construct and maintain the internet. But most of us think of cyberspace as not that, as something else. There are other objects, and those objects are connected together. They're not cell phone towers. They're not satellites. They're websites, and websites are connected together with links, or web pages, and they're connected together with links. So immediately, when we call up a particular information space like cyberspace, most of us have a conception of the structure of that space itself. Okay. Space and information space does not necessarily need to be completely virtual like the internet. There are lots of physical spaces, or increasingly more physical spaces, where we layer an information space on top. So an airport, if you physically enter an airport, it is an information space. You move through that space, and as you do, various information is revealed to you in terms of signs, timetables, objects, help desks, personnel, and so on. So when we're thinking about the information space, and this is related to our discussion about design, because in HCI you're often creating a new application, a new interactive system for which the information space has not yet been defined. If you're creating a website, then that website is part of an already extant information space, which is cyberspace. But if you're creating something relatively new, like a Leap Motion ASL educational game, what is the information space that lies behind your user interface onto the ASL game? What is the information architecture? What is the constellation of things that exist behind the interface? And what subset of those objects or relationships does your interface provide a view onto? One simple way to think about this is the information structure has all the structure, or has all the information architecture, and an interface usually is a projection of a subset of that underlying structure, right? So frame is one element in the information space you've been creating, but your users are probably not going to be aware of frame. There are three other objects, hand, finger, and bone. Those three objects, which are also part of the underlying information structure, those are visible to your user. Okay. As we're starting to create the underlying information architecture, the information space, we obviously, as always, are thinking about the activity that the user is trying to conduct through or in or with that information space. So let's take for a moment as an example an information space as a train station, which is a constellation of physical objects and informational objects. I'm moving through the train station. I see various trains, important objects that make up that space, but I'm also seeing a timetable, or I'm observing a timetable on my phone as I'm moving through the train station. Okay, so I picked the train station because it's pretty obvious what most people are doing inside a train station, which is catching a train or waiting for someone who's getting off a train. And in order to support that activity, there are a number of conceptual structures: routes, stations, times, railway car classes, what type of train is it, and so on. We can imagine paper interfaces, electronic interfaces, and so on. Okay. Obviously, many information spaces these days are extremely complex, and they may be hierarchical, meaning that they have different architecture, different structure at different levels. And an obvious example of this, again, is the internet. If you have a hierarchical information space, an interface at any one level of the information space is usually an abstraction of the level below. So we're seeing a more and more global view of the information space as we move out. If you're looking at Google Maps and you're looking at an entire country, you may be looking at the railroad network within that country. As you zoom in on a station, you might now see a constellation of important objects in a map representation of an individual station. Same thing with the internet. At the lower level of an individual web page, what is the information architecture of an individual web page? Well, it's made up of a number of conceptual structures, the things that make up that information space. Text, images, metadata, document structure, buttons, sorry, not buttons, that's the interface part. So the conceptual structure, the thing that is there, that is underneath the interface. Then we have the interface itself, which again provides a view onto a subset of the conceptual structures that make up a web page. For most people, in their browser, they do not see the console, right? You have lots of experience with that now. So the console are the metadata about the web page itself, not the text of the web page itself, but error messages or console messages being generated by the code that places the text on the page. That metadata is usually hidden from most users, but you can obviously reveal it if you want. Okay. We can imagine different interfaces onto the same space. So we have one web page. We can have the web browser view on a laptop onto that page. We can try and extract just the text and click something that will allow us to print that web page. Provides a different format, mobile device format for the page, and so on. So depending on, in this case, what device or the way in which the user would like to view the page, slightly different activities, 3 slightly different activities, that alters the kind of interface that, that reports the structure of that page to the user. Okay, we pull back out now to the, and we think of the internet as a whole, as an information space. It is obviously a space that is structured as a network. This was an old picture of the internet where each node here represents an individual web page or website, and obviously the edges connecting nodes represent links between pages. So what is an interface onto the net as a whole? Well, the obvious example is Google. You go and type in a word, and that word will reach into the space and pull out a subset of these nodes, not show these nodes to you in their network format, but rearrange them into a list where that list is sorted in a particular way, and it's sorted by an additional conceptual object, which is relevance to you. Okay, so if in the context of design, as always, this design process of going from the messy world of a bunch of frustrated users into a clean world of an information space that has been designed and created to support those activities, how do we go about starting to create that information space in the first place? So that is known as choosing an ontology, and I'll just skip ahead for a moment and come back. So what is an ontology? An ontology is determining what are the things that exist that make up a space or a system of thought. In our case, we're going to create an ontology for a new information space. What are the things that exist there? Okay, that's choosing an ontology. So way back in the very early days of computers, when the very first desktop interfaces were being created, there was this act of ontology creation where an ontology was created, and the first 2 things that were created were these things called files and folders. Why were those the 2 first conceptual objects that were formulated when this new information space of a desktop interface was being created? This was right at the beginning of personal computers, as we were moving from mainframes and punched cards to computers sitting on a desktop with keyboards and mice. There had to be an information structure, the thing inside the computer that was going to help somebody use this new thing called a personal computer. Why were the 2 first objects created in the process of creating that ontology? Why was it files and folders? as Sarah says, because most people were using them prior to personal computers. And the idea in the early days was that personal computers were going to support office work in some way, right? So in an office, two of the most common objects you see are files and folders and so on. So as we've talked about before, there was an attempt, first of all, to identify the A in PACT. What is the activity? Something to do with offices. And this concept of conceptual consistency. So if people are going to do office work, they usually do it by manipulating bunches of files and folders. Let's allow them to manipulate the same things on a computer. We'll create the same thing, but in a computer, files and folders. So an ontology is usually not created de novo out of air. The conceptual objects that make up this new ontology we're creating, they borrow for their conceptual objects from related tasks that were done in previous software or in other ways. Okay. What are some of the conceptual objects that make up your ASL system so far? You already have a somewhat non-trivial information space every time you start up and run your deliverable. What are some of the conceptual objects in there? So your code is written in JavaScript, and JavaScript or computer languages themselves are information spaces. They are made up of important conceptual objects like variables and loops and functions. But you're using those conceptual objects to construct a new information space. What are some of the conceptual objects that make up your ASL system so far? While you're thinking about that, let me add in lines representing fingers, okay? So the lines are part of the user interface, but representing fingers. So fingers is a conceptual object. It's actually a conceptual object borrowed from the Leap API. So what are some of the conceptual objects that make up the Leap API? What are the building blocks of a Leap software system? So fingers is one. Exactly. So hand is one. Bones is one. Bone is another. Coordinate is another one. Frame is another one. These are all the conceptual objects that make up the Leap information system. Your system, which uses that API, also has some additional parts to it beyond Leap. So you have something called a KNN. You have something called training instances and testing instances. So if you think about the ontology of your system as a whole, it's a combination of conceptual objects from Leap and from ML5. And additionally, when you get to your ASL educational game, you're going to be adding some conceptual objects. What are some common conceptual objects you find in an educational game? Regardless of whether it's teaching someone ASL, teaching someone typing, teaching someone a foreign language. What are some of the conceptual objects in the ontology of an educational game? You're going to have to organize your educational game so that you can help someone learn ASL. And you're not going to be presenting everything at once. You're going to walk them through the process of learning the 10 ASL digits. What are the parts to your system of that information space as they are moving through that space? They are moving from possibly complete ignorance of ASL to the end, which is that they are expert at the ASL digits. What do they see or what do they experience as they're moving through this ASL educational game? Not necessarily the interface, not the things we're drawing to the screen. What are the bricks and mortar of the system, the things that will hold it up? If you've ever tried to learn something in a tutorial or watched a YouTube video that's some educational in some way, it's usually broken down into bite-sized chunks. What are those chunks? So typically an educational game is broken down into lessons, right? So lesson 1, lesson 2, tutorial 1, tutorial 2. Usually there are exercises and tests and quizzes and so on. Test, quiz, question, answer, lesson, review. Those are all conceptual objects that make up usually our typical building blocks of an educational game. Okay, so hopefully you have the experience when you go into industry to actually create some brand new types of interactive systems in which it's not immediately obvious what those building blocks should be. So as we start to create an ontology, this is an important aspect of the design process. There are a lot of decisions you need to make along the way. Not just what are the objects themselves, files and folders, variables, loops, and functions, hand, finger, bone, but what is the right level of abstraction? So we could, for example, create an ontology in which there are just a few things. For example, if you're going to create an educational game, you're going to have to choose the level of abstraction for your game. You might choose very few conceptual objects. You're going to have lessons and tests. That's it. Just 2. Okay. That's known as a coarse-grained ontology. You're choosing relatively few categories, lessons and tests. Those categories are weakly typed, meaning what do you mean by lesson? So let's go back to our example of a train station. People are interested in catching trains in a train station. So the conceptual object that should most obviously leap to mind is trains, or train, let's say. We're going to define this category as train, and it's going to have 4 parameters or 4 modifiers. What station it leaves from, at what time, what station it arrives at what time. But this is relatively vague. It doesn't tell us what type of train this is. Is this a regional train, meaning it's going to stay within the same country? Is it a transnational train? Is it moving from one country to another? So the drawback of a coarse-grained ontology is that we have these vague category descriptions and these relatively complex objects. They need a lot of material attached to them. So what happens if a user comes to your ASL educational game and they see a series of lessons? They want to take beginning lessons. They don't know ASL. Where are the beginning lessons? Maybe it's hard for them to search through the lessons that are available for them to click on, which ones are for novices, which ones are for advanced users. So it may be hard for them to search for that. The advantage is that for us as the designers, it's easy to classify these various objects. We know where to put things in our ontology. So if our users are confused about beginning or advanced lessons, maybe we make our ontology a little bit more fine-grained. We take our conceptual object and break it into 2, beginning lessons and advanced lessons. Or in the case of our train example, because the user perhaps is having a hard time figuring out which train to take, because some trains might be cargo trains and some might be people trains, let's create many different categories. So we're going to have 4 types of trains: express train, first class train, cargo train. The extent of the train, is it local, state, or national? Perhaps we start to add some additional details about when it's stopping, if it's stopping, and so on. This allows us to then organize things. So we could have a timetable of express trains, a separate timetable for regional trains, a third timetable for international trains, and so on. So for any given instance, we know exactly where it needs to go, which category it fits into. On your ASL educational game, when somebody arrives, maybe you ask them if they know some ASL or if they don't. If they know some ASL, they're able to see the advanced lessons. If they're new to ASL, they only see beginning lessons. However, now we've got a lot of categories and things are spread out, so hard to find the right category. Somebody arrives at the train station, they don't just see one timetable, they see multiple timetables. So which timetable are they supposed to be looking at? It might also be hard to find, in some cases, the category for an instance of one of these objects. So what happens if we have a train that is both an express train and a first-class train? Do we add that train to our list or our timetables of first-class trains? Do we add that train to our timetable for express trains? In this cartoon example, maybe it's relatively simple. We put the same train in both lists, but that can be confusing because now that train is in both lists. Are those separate trains? Is it the same train? That train probably has an ID number, so I got to match the ID number of that train with the ID number in that train. Is this actually, in retrospect, making things more difficult now for the user to do what they want to do, which is find a train and catch it? So there's pros and cons to deciding on the granularity of an ontology. Okay. So let's go back to this slide here. We're disentangling these words here. What is an ontology? We're deciding what are the things that exist. In my ASL educational game, I'm going to have hand, fingers, and bones, and lessons and tests. Once we decide on an ontology, we can then also start to construct a taxonomy, which is how to organize instances of these conceptual objects. So how to go about grouping things together, deciding on a method of classification. So an easy way to think about ontologies and taxonomies is that in terms of our laptops, we all have exactly the same ontology. We all have files and folders, but we probably all have different taxonomies. So in my case, my file system is arranged at the top level by calendar year, 2002, 2003, up to 2020. Inside each year, I have a subfolder called Research and Teaching, and those subfolders repeat every year. That's how I track research and teaching for myself from year to year. That is probably not the same taxonomy that you have. We all have files and folders, but we organize them into different taxonomies. What are some of the different taxonomies that you all maintain? How do you organize your file system? If you organize it. For some people, it's just drop all files in the top level of your file system and use search to find the files that you want. Now that desktop search has gotten so good, maybe you don't need a taxonomy. Maybe it's not so necessary to try and organize things into subfolders of subfolders of subfolders. I organize mine at the top level by year and then research and teaching every year. How do you organize your file system? Maybe that's a somewhat personal question. Maybe that's not something that people want to share with the rest of the class. That's fine. I think you get the idea here. Courses, projects, and employment. Okay, from a student's point of view, that makes sense. Class, homework, projects, notes. Yep. School folder. Absolutely. Yep, that makes sense. Organized by semester. Yep. and then by course, and then by assignment. Yep, that makes sense. You can imagine that for most of you, for most students, you probably have similar taxonomies. Your taxonomies are quite close to one another. They're probably close to mine, a professor, but slightly different. We both are involved in the same high-level activity, which is participating in a university, but obviously our activities are slightly different, and that's reflected in our slightly different taxonomy. Okay. If someone is, depending on your ASL educational game, you may allow your users to save state. They may be able to save where they are. Your system is going to eventually maintain data about different users of your system, so users can see where they are relative to other people. You might actually, as you construct the ontology for your ASL educational game, you may allow a given user who uses your system to create and rearrange their own taxonomy. Which lessons have they completed? Maybe they want to select a bunch of lessons they want to work on tomorrow. They move that into their own local folder, and so on. Okay. So if you're building an information space, in the process of designing this information space, this is clearly an ontological exercise. We're creating the things that exist. And then once we've decided, for example, on a coarse-grained approach, we might also, as designers, perform a taxonomic endeavor. So I've decided in my ASL educational game that I'm going to have lessons and tests. But how many lessons are there going to be, and how many tests are there going to be? Am I going to arrange the lesson plans for each user so that they do 2 lessons, then they take a test, another 2 lessons, then they take a test, and so on? That's a taxonomy. That might be something that I bake into the system, or I may turn over the task of constructing a taxonomy to the user. They can take any lesson at any time, and they can take any test at any time, and they can create their own schedule. I'm going to take these 3 lessons today, finish with a test. Tomorrow I'm going to schedule for myself these 6 lessons and then take a test. Okay. The final term here is epistemology, and this takes us into philosophy, the philosophy of knowledge. Where does knowledge come from? A great example of an epistemological question is, was math invented or was math discovered? What is the nature of the knowledge? What is the nature of mathematics? Does it count as truth, or is it something that people made up and agree on? Those are all epistemological questions, very philosophical. What does that have to do with HCI? Why did we choose a particular ontology over another? This is, remember, design philosophy, where design philosophy is a belief about what is a good way to design an information system compared to a bad way. You might ask 10 information designers, and they may all agree that for a given activity, a coarse-grained ontology is better than a fine-grained ontology. There's some sort of general agreement about the best way to create an ontology for a new system. Why is there that consensus? Is that because that's just the right way to do it, or is there some sort of belief? We're not going to talk too much about epistemology, but it's important to know that one of the most difficult and exciting things about working in HCI is you're often bringing new things into existence, things that didn't exist before. How does that process occur? Where does it come from? Okay, let's take a minute and practice ontology and taxonomy. I want you to think for a minute and then type into chat different domains and what are some of the conceptual building blocks of those domains. So, for example, politics is a domain. There are conceptual objects like votes, candidates, campaigns, posters, and so on. If you're a campaign manager for a candidate, you might come up with a particular taxonomy. How is that campaign going to be populated with meetings and votes and turnout, handshaking events, policy formulation, and so on. So that's a domain, politics, and a little bit about ontology and a little bit about taxonomy about that. So I want you to think about all the different kinds of domains that are out there. They don't have to have anything to do with computers. Sports is another domain of human experience, art. What are the conceptual building blocks that make up those domains? Not necessarily things you can touch, like a vote. And what is the taxonomy that typically exists in those domains? Okay, I'll give you a minute or two to think about that and type some ideas into chat. Okay, in the interest of time, let's move on. So please, if you're typing something into chat, just finish it up. And I'd like to see what ideas you came up with. Okay. All right. I'm going to move on. If you're typing, please do finish up. We'd love to hear what you came up with. Okay, we're going to finish lecture 9 by thinking about some of the characteristics of an information space. We've talked about granularity already. Do we have a large number of conceptual objects that are very clearly defined? That's a fine-grained ontology. Do we have just 2 or 3 objects, like files and folders? And they're very general in their description. Again, thinking about how to design this space. Thank you, Prasida. In thinking about that space, as always, we're going back to PACT. We're going back to the people that are going to navigate that space, the kinds of activities they want to try and perform in that space, and what is the context that surrounds them. Let's think about volatility. So now we're thinking about the data that is in that space. How often do types and instances of objects change? So we have a first-class train that arrives at its destination. It rests there. Everybody gets off. Everyone gets back on. Is it still a first-class train, or is it renamed something else? If it's a regional train, when it ends its current route, does it become an international train? How volatile are the tags that we are tagging these objects with? We want to choose the granularity, for example, based on this activity of volatility, right? So if things are volatile, we probably want to keep a very coarse-grained ontology. We're just going to deal with these things called trains. And the types of trains and where they are and where they're stopping is changing quickly. So we'll just add that as a tag to the name of this concept, which is train. If an international train is always an international train, first-class train is always a first-class train, then maybe it makes sense to have this fine-grained ontology where we have lots of different types of trains, because a train doesn't change its type very often. Okay. Priscilla said sports. So sports competition. That's a great example of an important concept in the space of sports. The governing body, solo or group competitions. Exactly. So Sarah says in terms of artist or an art, we have materials, color theory. Exactly. Those are conceptual building blocks. Color, form, movement, substrate, palette. These are all things that are related to at least painting or fine art in particular. Taxonomy is how to group colors together. Exactly. Great. I think you get the idea. Okay. What is the size? What are the number of instances of these objects in that space? So we might, if we choose a coarse-grained ontology, we end up with lots of object instances. So if we have just files and folders, on my machine I have probably tens of thousands of files and thousands of folders. If I choose a fine-grained ontology, I have many fewer instances of each individual object type, right? This can just this choice alone of altering the size or the number of instances affects a particular activity, which is important in an operating system, which is search, right? So if I have a coarse-grained ontology, then I need to have search methods that are tuned to be able to find data within very complex objects. If I have a fine-grained ontology, my search method should be tuned to locating simple objects. So, for example, let's imagine we have a website that has lots of pages. So we have a fine-grained ontology. We have lots of different types of pages in this space. We have lots of different types of pages in this website. So it makes sense to search across links. If we create a website that has a coarse-grained ontology, it has just 2 or 3 pages, but each one is very long and is broken into subsections, and each subsection is broken into a further set of subsections. Then I have few complex objects, coarse-grained. And I'm going to need to search that page. I'm going to provide interfaces that allow for searching within objects. So scrolling the page, text search within the current page, and so on. Again, just a bit of a cartoon example, but showing that how making different choices about an ontology affects activities. The activities performed in that space. Okay, so we've been focusing for the moment on conceptual objects, the things that don't physically exist: files, web pages, color theory, competitions, votes, candidates, and so on. Those are all the conceptual objects. As we start to create our user interface now, our view onto that information space, how does somebody interact with that user interface? Well, we have the conceptual objects behind the interface, quote unquote, behind the interface. And then the user is in front of the user interface, and they are manipulating input and output devices, storage devices, and so on. So we got physical objects being manipulated by the user to alter the user interface. And we have the conceptual objects behind the user interface, and a subset of those conceptual objects are being projected into the user interface. And where they meet, and where we're spending most of our time in this course, is at the midpoint, where we have perceptual objects: windows, web pages, icons, widgets. So if you have a GUI, a visual representation of your operating system, files are usually represented as icons, right? Or you can click on one, and that icon, that localized piece of space, expands into a 2D projection, which is a window into that file, or a window into that folder. Okay, so as always, we're trying to make a good match between the physical objects, or the things on the front of the interface, and the conceptual objects behind the interface. Sarah, I think, already mentioned a good example of that earlier, which is files and folders. So that makes sense. There are physical files and folders, and we have a visual representation of files and folders in a GUI. So that's a good match. It is often easy to get trapped in a poor match. So what would a poor match between a perceptual object and a conceptual object be? Let's imagine that we have a conceptual object in our system, which is a network. So you could sit down with a friend and decide you want to try and map out the structure part of Wikipedia. So Wikipedia is obviously a connected set of pages. Your friend works on storing in a spreadsheet a series of Wikipedia pages and the links between them. So they're storing basically the part of a graph, nodes and edges, in one file. You work on another closely related part of Wikipedia. You store that in a spreadsheet. So you now have two files, two different spreadsheets on two different machines, you and your friend's machine. And you're storing two parts of a bigger network, Wikipedia, as two smaller networks. But if you're both scraping similar parts of Wikipedia, it's probably likely that there are links from the part of Wikipedia that your friend grabbed that point to the part of Wikipedia that you grabbed, and vice versa. So you're pulling out a sub-network from Wikipedia and breaking it into two different files. But if it's something that is densely connected and they're in different files, that's not a good, those two perceptual objects, those two files are not probably good representations of that thing. Alternatively, if you're scraping Wikipedia and you're grabbing very distant parts of Wikipedia, meaning that there are few links between those two sets of Wikipedia pages, it makes sense to store them in different files. Yeah? Okay. So speaking of links and edges, when we start to think about an ontology, we then start to think about the topology of that ontology, or that topology of that space. For our purposes, topology is just going to mean what is connected to what. Okay, so let's take an ontology that's populated with animal, human, rock, and planet. Those are the four building blocks that make up this information space, or this ontology. Immediately, if you were to ask people, most people would tell you something about distance or connectivity between these four concepts. Animal and human are quote-unquote closer to one another than animal and planet. People could probably give you an explanation for why animal and human are closer to one another than animal is to planet. How do we know that? Well, we know that because we're evolutionarily related to other animals. If you take another information space with other conceptual objects, it's interesting to think to yourself whether you know what the topology is. What is the underlying structure of that system, of the conceptual objects that are in there? How is it distributed? So let's take Wikipedia. Most of you have probably used Wikipedia for years. You may or may not have some sense of the underlying structure of Wikipedia. Let's test that for a moment. Obviously, Wikipedia is a network. It's a set of pages that link to one another. Wikipedia is itself a network that sits inside of the larger network of the internet. Is Wikipedia more densely interconnected than the internet as a whole? Meaning, if you were to visualize Wikipedia as a network, a bunch of nodes and edges, are there more edges between all that nodes? Is it a denser ball of yarn than the internet as a whole is? In the case of Wikipedia, let's just assume links that point to other Wikipedia pages, not pages within Wikipedia that point to pages outside of Wikipedia. Is Wikipedia more densely interconnected than the net? Okay, Joseph says yes. Joseph, if you don't mind, what's your reasoning? Do you think that, or do you know that? You could probably write a script, for those of you that know how to write web crawlers, that could start to give you an estimate of that. Okay, as Joseph mentioned, about 95% of Wikipedia pages have link chains that lead to the philosophy page. So Joseph, you've stolen my thunder here. That was going to be my next question. We're going to talk in a moment about distance and direction, navigating through Wikipedia. So what does it mean to move up or down or left or right or forward and back in Wikipedia? It probably doesn't make much sense. Wikipedia doesn't really make sense to think of it as occupying a three-dimensional space. Your ontology that you're creating for your ASL educational game, there definitely is a left and right and up and down and forward and back. But in Wikipedia, there is actually a particular direction that you can move in, which is towards the center or towards the rim. And I was going to ask you, what is the center of Wikipedia? Joseph has already told us. There are a number of Wikipedia games that you can play. One of them is to open a random Wikipedia page. Click on the very first hyperlink in the page, as long as it's not a hyperlink to metadata, but an actual link in the body of the text of a Wikipedia page. Typically, it'll take you to another Wikipedia page. You click on the first hyperlinked word in that page, and you continue. Eventually, with relatively few clicks, you'd be surprised how few, you will typically end up on the philosophy page. This was clearly not something that was planned a priori by the Wikipedia designers, those that created the ontology of Wikipedia. It's an emergent property of the collective construction of Wikipedia. Okay. Ethan says, as pages get more obscure, it's harder to backtrack. Okay, we're going to focus on that word backtrack for a moment. So what does it mean to reverse direction in an information space? One thing your user might ask as they're moving through your information space in a particular quote-unquote direction, can they turn around and go back? An important direction once you turn your system into a game or an educational game, direction should hopefully be moving towards greater proficiency in ASL. Can they turn around and go back and to relearn something? Github is another great ontology. It's got some great conceptual objects in there. While I'm describing GitHub, please type into chat the conceptual objects that make up GitHub. Some of you have gotten stuck in your deliverables. One of the nice things about GitHub, if you know how to work with it, is being able to roll back your work, to undo your work to that point where it was working before, throw away your most recent work, and start moving forward again. The deliverables help you to do that because all the steps are enumerated. So hopefully you know, okay, everything was working on step 53. I'm now at step 56 and things aren't working. I'm going to go to GitHub and just roll things back to step 53 and then start moving forward again. It's part of why GitHub was designed, to help that process of reversing direction, going back to a particular point and moving forward again. Repos, right? A repo is a noun that wasn't very familiar before Git was invented. Very important, right? So commits and merges, those are other conceptual objects that didn't exist before GitHub. The GitHub designers, they sat down and created a brand new ontology that is held up by repos, commits, merges, and so on. Okay. So aside from the topology, which is what is connected to what, we can also ask distance. So how far apart are two objects? Usually in an information space, that's not literal distance. But harking back to our discussion on Tuesday about measurement and metrics, there are different ways that you could measure distance in an information space. So in Wikipedia, it could be how many clicks go from page A to page B. So if I give you two random Wikipedia pages, I could ask you what are the fewest number of clicks staying in Wikipedia space that will take you from A to B. We could measure the number of clicks, but probably more importantly is how much time does it take you to figure out what that shortest path is? How long does it take you to navigate? If you're sitting at A in Wikipedia and you're trying to get to B, how long does it actually take you to get there? You might need to actually read the text that the page you're on to make an intelligent guess about which link to click on next. Right? So number of clicks, number of links, number of times the user reverses direction and goes back. How many times do they go back to A and try and click through to B again? And what does it mean to reverse? How does somebody what is the meaning of getting lost in an information space? And what does it mean to find your way again or save your place in a particular information space? You think about something like YouTube. It is in essence a one-dimensional the structure of YouTube is one-dimensional because the one thing that most people care about is a video. Where are you in that video as a function of time, right? You can save your place in a particular point in a YouTube video. If you have a branching topology, if you're in an information space with a number of branches, up and down is not necessarily clear. So as just an example of this, if we assume that you're navigating through the internet and you're using the forward and backward buttons on your browser, if you're on page A and you click a link that takes you to page B, you're on page B, you go back, you click back on your browser window, which takes you back to page A. Now you click a separate link on page A that takes you to page C. You hit back on your browser button, and now you hit the forward button on your browser. You're sitting on page A, you hit forward on your browser. Which page does it take you to, B or C? You went from A to B, back to A, to C, and from C back to A, and now you click the forward arrow on your browser. Does it take you to page B or page C? For every single browser these days, it always takes you to C. Why? You were recently at B and C. Why is it always C? What's the rationale? What's the thinking behind that? In older versions of browsers, that wasn't always the case. But there's been a gradual consensus that in that situation, A to B, A, C, A, forward should always mean C. How come? If you look at people's navigation traffic as they move from page to page, or for those of you that are in campus dorms and you can look out at the campus, if you watch a large number of people walking around a physical space, if they reverse direction, they often turn around and now go in the same direction that they were going at just previously. So as Joseph mentions, C is obviously the one that they most recently visited. And because of human behavior, there's something about reversing direction that when you turn around and start going quote unquote forward again, you often want to go in the direction that you were the previous direction in which you were heading. You're on an unfamiliar campus, or you're in an unfamiliar city, you go partway down one street, you back up, you go down a different street, you come back, you think a little bit. You're often going back in the direction you wanted to go before. You might click on a link that takes you to D. You might not have been happy with B or C and you want to go in a different direction. I went to C. I didn't spend enough time there. I wasn't paying attention. I went back. Now, what was that C again? Let me just check. There's something about human behavior in terms of navigating complex or unfamiliar spaces that reversing direction, most people tend to want to go when they go forward again in the direction that they were most recently heading. That is, again, a conceptual consistency with navigation in physical spaces that has brought into helping with navigation in virtual spaces. Okay. So if someone is in a virtual space, like a computer game, a physics engine, something like that, we might again use visual analogies or visual metaphors to help them to guide 3D navigation. If you're walking around in a natural environment, the woods, a field, a rural landscape, you're often paying attention to landmarks, the horizon line, and so on. So can we borrow some of those visual metaphors to help people navigate through information spaces better? Okay. As people are navigating through an information space, what aspects of their sense organs can we exploit, right? So typically we are projecting to our visual system, our eyes, but they might also be listening to something as they are navigating. And if somebody is moving through a physical space, there are certain expectations we have about the physical world as we move around. You remember this right from the beginning of the course when we were talking about trying to support people's intuitions. If someone is moving, they're moving through the internet or moving through a virtual space, what are things that happen when you move in physical spaces that we can project or support in a user interface? I'm going to show you one early example where the user interface is very carefully constructed to support the illusion that you're moving through a three-dimensional space.
Hi, my name is Johnny Lee. And in this video, I'm going to show you how to perform head tracking and create desktop virtual reality displays using the Nintendo Wii Remote. Now, first, what do I mean by a desktop VR display? Well, when you think about most computer screens, they're typically used to display a flat image, a little bit like this picture in this picture frame. Even if the picture is of something 3D, like a video game, the picture is still flat. So it doesn't change depending on what angle you view the screen at. A desktop VR display, however, is a little bit like taking the picture out of the picture frame and then just having the frame. Now the scene actually changes depending on what angle I view the screen at. So this essentially becomes a portal or a little window into another room. Now to do this, the computer needs to know the location of your head relative to the screen, and this is called head tracking. Now to perform head tracking, we're going to be using the Wii Remote and the sensor bar, but we're actually going to be using them backwards. We're going to put the Wii Remote next to the TV and actually move the sensor bar instead. The Wii Remote actually contains an infrared camera, and the sensor bar is simply two sources of infrared light. When the camera sees the two dots of light, it's going to give an approximate location of my head horizontally, vertically, and in distance from the screen. Okay, the tricky part is now we're going to have to find some way to mount the sensor bar onto our head. One common trick is to get a baseball cap and then mount the hardware to the cap. And this is definitely going to work, but it's a little bit goofy. So instead, some hardware stores sell these safety glasses with LEDs built in on the side meant to be used as headlamps. Now, if you replace the LEDs with infrared ones, you essentially get your head-mounted sensor bar and a nice, sporty safety goggle form factor. Once we've created our head-mounted sensor bar and I've connected my Wii Remote to my PC, we're ready to do some head tracking. Behind me is a demo program of a 3D room with some targets floating in it. Now, because the effect only works for the person wearing the sensor bar, I'm going to have to show you the effect through a moving camera. Now, to do this, I'm literally just going to hold the sensor bar at the base of the camera and move it around. Just a quick note, to power the sensor bar, I simply turn on my Wii after I've connected my Wii Remote to my PC. First, I'm going to show you what it looks like without head tracking, which is what displays normally look like. You can see that although it's a picture of a 3D room, the image looks very two-dimensional and bound to the surface of the TV. Now with head tracking turned on, the TV actually looks like the entrance to a real room. Just like in real life, by moving our head around, we can look behind objects. And if you look really closely, some targets actually appear to be floating out in front of the screen, reaching into the real world. If we get closer to the screen, we get closer to the objects, and we can even get behind the ones floating in front of the screen. As I pull the camera back, keep an eye on the frontmost target. Head tracking provides the illusion that the target is actually floating directly above the laptop screen, far in front of the TV. Now, using this picture of a football stadium, if you move right, you can see more of the field. If you move left, you can see more of the stands. And if you get closer to the screen, you see more of everything, just like a real window. If I use my IR glasses and keep the sensor bar on the TV, I can use a second Wii remote to point and shoot like any Wii game while also doing head tracking. So now ducking and shifting your body is actually meaningful to a game. You can also see now how the perspective is incorrect if you are not the one wearing glasses. So head tracking for VR displays is only going to work for one person at a time. But for that one person, the 3D experience is going to be far more realistic and immersive than anything else we see in homes today. So if you're watching this and you're a Nintendo Wii game developer, I want to see some games. Anyway, as usual, you can visit my website to download this software and find out more information about my other Wiimote projects.
Okay, so that was Johnny Lee showing us his head tracking software and begging Nintendo Wii developers to develop games around this after. This video is quite a few years old now. Nintendo was actually listening, and Johnny Lee now never has to work again. Okay. So let's talk a little bit about this head tracking system. What expectations of moving through physical space is being supported by this head tracking system? What happens with your visual system? What do your eyes register when your body moves? Parallax of objects, right? So parallax is this idea that objects that are close to you move faster than objects that are further away. So parallax is about velocity, right? What is the speed of travel of objects, or the seeming speed of travel of objects relative to you as you are moving? As you could have seen in that video, objects that were closer to the user were definitely moving faster on the screen than objects that were further away. That's velocity. What about direction? Which direction do objects move when you move? How would you code up this system? How would you determine the velocity and the direction of movement of these objects? Remember that your eyes don't directly detect the 3D structure out there in the world. There are flat sheets of photons falling on the surface of your eyes. Your brain is reconstructing the illusion of 3 dimensions from the 2D shower of photons falling on your eyes. And we need to make sure that those photons are falling in the right way to convince the user that they're seeing a 3-dimensional world. So as perceidimensions, of course, that if you move to the right, objects all move to the left, right? So objects are all objects are moving in the opposite direction from your motion, but their speed of travel is different depending on their distance from you. Okay, so as Johnny Lee mentioned, we need to sense the relative position or angle of the observer's head from the screen as they move, and that alters the drawing of the objects. He mentioned during the video that in order to see this 3-dimensional illusion, you have to wear those glasses, right? The system has to detect your head moving. So if you have a friend who's playing a game with this system and is wearing the glasses, from that user's point of view, the game is 3 dimensions. This is 3-dimensional, but from you, the observer watching the same screen in the same game, it looks 2-dimensional, right? Because the system is not detecting your head motion. However, when you were watching this video, you obviously were not wearing these glasses, and hopefully for most of you, you could see the 3-dimensional structure. So that seems to that seems to go against what Johnny Lee was saying. You weren't wearing the glasses, but you saw the three-dimensional scene. You saw the two-dimensional scene as a 3D scene. How's that possible? This is definitely an optical illusion. We're going to talk much more about optical illusions next week when we talk about cognitive psychology. But how is this possible? How could you have seen this scene as a 3D scene even though you weren't wearing the glasses? He just said that only the person wearing the glasses can see the scene. I'll give you a hint. There are two optical illusions going on here. There is the one for the person that is wearing wearing the glasses, or as Johnny was demonstrating, for the person that is moving the camera. That's one optical illusion, but there's a second one on top of that one that allowed you to see in 3D even though you weren't the one wearing those glasses. If you were on the shoulder of the person, okay, yes. So all of us, as we were watching this YouTube video, your brain was simulating you sitting on the shoulders of Johnny Lee. A video itself is an optical illusion. If the person who is holding the camera and shooting the video, like Johnny was doing, your brain is watching that video and everything in that video is moving left and right, and some objects in that scene, in this case, are moving faster than others. When your brain sees that, it projects into the scene. It feels as if you are the one that is moving. And so basically you have those two optical illusions lining up and convincing your brain you are the one that's moving and those objects are not moving. They're simply moving relative to you. They're stationary and they're moving relative to you. We're going to talk about this quite a bit on Tuesday when we talk about mental models. Your brain is making predictions about what it expects given what it's seeing. So if your visual scene is eaten up mostly by the video and the camera is moving, that is convincing your brain. Your brain is being convinced that it is moving. What are some situations, let's go back to the C impact analysis context. What are some situations in which you are moving, or your brain feels as if your body is moving, but there is no parallax, it's not happening. This pattern is broken. I move and all the objects move relative to me. What are some conditions in real life, again, forget looking at computers, where this occurs? Mona Lisa's eyes, yes, seem to follow you as you're moving. I guess that would be an example of that. Any of you have ever run on a treadmill? You are moving, or all the strain sensors in your body, all of your muscle systems, your internal or interoceptive senses are recording that you are moving, but the visual scene around you is not moving. It is maybe jumping, it is moving up and down, but there is not a continuous flow of information. Your body feels as if it's walking or running, and for 99.99% of your waking experience over your whole life, whenever you are walking or moving, objects are flowing past you. That expectation is very strong. There has been, until you step onto a treadmill for the first time, for most people, they have never had that experience before of movement, but lack of parallax or lack of relative motion. If you walk or run on a treadmill for even a few minutes and then step off the treadmill quickly, what happens? Actually, Cole's example of riding in a car while reading leads to the exact same result for a lot of people as stepping off a treadmill quickly. Motion sickness, right? As the name implies, motion sickness. Why? Why this motion sickness? Well, again, it's actually not that well understood, but it is clearly your body's reaction to the breaking of a very strong expectation. Your brain has built up a very confident prediction about what will happen in your visual scene when your body registers motion. And if that expectation is broken, for some people, their bodies have a very strong reaction. So this is just a warm-up for our discussion next week about cognitive psychology and mental models. I think I got 1 minute left, so I just wanted to show this more recent tweet that I actually saw yesterday or 2 days ago. So this is an updated version of Johnny Lee's system. Again, we are not wearing any special glasses. How is this working? Given our discussion about head tracking, how is the iPad casting the illusion that we are looking into an empty box? Actually, there's 2 iPads here, as you can see. How does this work? So the iPads have a camera. Those cameras, the camera in the iPad can see the observer. And as Priscilla mentions, the camera in the iPad is tracking where the user is standing and updating the visualization appropriately. Okay, I think we will stop there. You will have a quiz tonight. Just a reminder, there was no quiz last Tuesday. Good luck with Deliverable 6. I wish you all a good weekend, and we'll see you back here on Tuesday. Thanks very much, everyone. Bye-bye.